All right, we're back with the final lecture for chapter 1. In this final lecture, we've already covered Lewis structures, the electronic structure, and then the molecular geometry of the different atoms. So how we can kind of predict the shape of molecules based on their formula. And now we're going to use the shapes that we understand to predict different properties, specifically polarity and solubility. Those are going to be the two main outcomes of what we want to kind of review from Gen Chem. All right, so that brings us to valence shell electron pair repulsion theory, or VSEPR theory is how I usually call it. Basically, this valence shell electron pair, the valence shell could either be a shared pair of electrons, so a bond, or a lone pair of electrons. And the idea is basically these bonds or these lone pairs are collections of electrons, and electrons are negatively charged, so they're going to repel each other. So as a brief review, hopefully you remember this from your Gen Chem, but if not, we are going to review it very, very briefly here. The way that we figure this out is we start by counting up the steric number, and that's just the total number of sigma bonds that the central atom has, and its number of lone pairs, and we just add those two together. So if we look at methane here, we see that methane has 1, 2, 3, 4 carbon-hydrogen sigma bonds. So that's 4 sigma bonds, 0 lone pairs on our central carbon atom. And again, we are only evaluating this for one atom at a time, so just keep that in mind when looking at carbon. So overall, we have a steric number of 4. Now, if we look at ammonia, NH3, that has a central nitrogen, so we're looking at the nitrogen. It's got 1, 2, 3 sigma bonds to 3 different hydrogens, and then a lone pair, 1 lone pair on that nitrogen. So that becomes 3 plus 1, or the same steric number of 4. H2O, central oxygen, has 2 lone pairs and it has 2 sigma bonds. So again, steric number of 4. Now, this is where we're going to kind of take a shortcut in terms of organic chemistry. Once we count the steric number, we can actually figure out the hybridization of whatever that central atom is. So if we have a steric number of 4, then we know that our molecule is sp3 hybridized. If its steric number is 3, then it's sp2, and if the steric number is 2, then it's sp hybridized. And the reason that we can know that is because this is going to tell us the number of hybridized orbitals you need to accommodate the electrons that are in that central central atom. So each of these ones that we saw had a steric number of 4, so methane, ammonia, and water. And sure enough, they are all sp3 hybridized. Now, that is that's the hybridization. Now, we want to keep in mind that we have this sp3 hybridized atom. It's got 4 valence electron pairs, and this is going to give us the general group, which is a tetrahedral electron group geometry. This is distinct from the molecular geometry because in the electron group geometry, we consider the position of the lone pairs. In the molecular geometry, we're not going to look at the lone pairs because the lone pairs are basically invisible when we actually image the molecule itself. So here we have 4 equal bonds, so everything's equal, and so it's a tetrahedron. So that gives us a bond angle of 109.5 degrees between each of our atoms, each of the bonds. Now with ammonia, there's a lone pair. The lone pair is like a stronger negative charge, so it pushes a little harder on these NH bonds here. That actually shortens the bond angle pretty significantly from 109.5 predicted to 107 actual. And then finally with water, we actually have 2 lone pairs. Those are both pushing even harder on these protons, the oxygen-hydrogen bonds. So now our angle is even more acute at 105 degrees. Yeah, so again, this is all just kind of review here. If you have a steric number of 4, you have a tetrahedral electron pair geometry, and then you could have a tetrahedral in the case of methane, trigonal pyramidal in the case of NH3, and then bent in the case of water. So that's just something to recall. Looking at steric number of 3, for example, we have BF3. Now, this isn't something that we're going to see a lot this semester, is having like a boron. The more common sp2 hybridized molecule that you're going to see is a carbon-carbon double bond, so C double bonded to another C. That's going to be the more common sp2 hybridization. That's what we looked at when we covered the hybridization though. So this is kind of just giving you a general idea of the molecular geometry. I just want to kind of point out where this is headed. Because this is more like a inorganic or a general chemistry thing that we're going to see. So here with BF3, boron is bonded to 3 different fluorines and it has 0 lone pairs, the steric number of 3, and so it's sp2 hybridized. So yeah, so what that ends up meaning is like these push themselves to the corners as far away as they can, and sure enough, that's at a 120-degree bond angle here. You can also imagine a steric number of 2. Here we have beryllium hydride. Now, more commonly, again, this is going to end up being a carbon triple bonded to another carbon, or for example, to a nitrogen. It's less likely that we see sp hybridization from, for example, beryllium, but this is just an example, so keep that in mind. Here, beryllium has 2 sigma bonds here, so 2 beryllium hydrogen sigma bonds, and so it's going to be steric number 2. The geometry ends up being linear because this is an sp hybridized atom. Okay, now to follow up, let's go ahead and go to our sample exercise 1.6. This is where you're going to draw a Lewis structure for CO2. And what I want you to kind of ask yourself is, what's the hybridization on the central carbon? And then what happened to the p orbitals? Are the p orbitals empty or are they going to be full? So take the time, pause the video, get sample exercise 1.6. I'm also going to be posting a video of me solving that problem later on. So you can pause the video now and we will carry on with the lecture. So yeah, here's our overview of molecular geometry. If you have steric number 4, then you end up with a sp3 hybridized central atom, which is a tetrahedral electron group geometry, which could be either tetrahedral, trigonal, pyramidal, or bent, depending on the number of lone pairs on the central atom. If you have a steric number 3, that's sp2 hybridized. So it's trigonal planar electron pair geometry. There's no lone pairs, it's trigonal planar, and then if there's 1 lone pair, it's bent. Now here, we just kind of like overlap the 2 bents. That's not exactly true. The trigonal planar bent or the steric number 3 bent should have an approximate bond angle of like 118, closer to 120, compared to what we saw for water, which was 105. So it's distinct, but kind of a minor point. We're not going to run into that much this semester. That's why we're kind of going quickly through it. And then finally, steric number 2, that's sp hybridization and a linear electron pair geometry with a linear geometry. Okay, so now this is where things actually get important. We use all of that knowledge of Lewis structures and VSEPR to figure out whether or not our molecules are polar and what are the dipole moments of those molecules. So remember, we covered this in the last lecture where electronegativity differences give us polar bonds. And there's also this idea of induction. We'll talk about that when we talk about, in particular, when we talk about London dispersion forces here in just a few minutes. But the idea is you can induce a dipole by having a dipole next to an atom. Okay, so the dipole moment, this is going to just tell us like how polar is a molecule. If you have a completely nonpolar molecule, like hydrogen, let's say, the dipole moment is going to be 0. And that's going to fall out from this equation where the dipole moment is equal to the amount of the partial charge in the polar bond times the distance that the 2 charges are separated. So basically, you can think of this like the bond length, right? So this is the bond length, and this is how big is the difference in electronegativities. If the differences in electronegativities is large, you're going to have a bigger partial charge, and so that would result in a bigger dipole moment. Similarly, if you have a longer bond, the longer the bond is, the more that is going to increase the dipole moment. So just kind of keep that in mind as well. But it's got to be the multiple, and you have to multiply both of them. Oh yeah, these are reported in a unit called the Debye. It's named after a chemist, capital D. And then yeah, we just have some conversions here to the elementary charge unit. But we're not gonna be really that important. Okay, here, let's actually look at what is important, which is predicting the polarity of a molecule just from its structure. So if we consider, for example, chloromethane, so this is a methane molecule that has just a single chlorine atom on it. So we've taken one of the hydrogens and replaced it with a chlorine. The way that we can do this is we can measure the charge on the chlorine atom and on the carbon atom, and whatever the magnitude of the charge is, and multiply it by the distance. Now notice here, we just kind of plug those numbers in. On the test, for example, you'd have to be given a bond length. The bond length is what you could plug in here for distances. And then the elementary charge, like we would also have to show you that charge. So now the charge separation is, it's a covalent bond. So it's not like the electrons are completely separated onto the chlorine and they're completely left the carbon. They're shared between the two, but we know that the chlorine is just pulling a little bit harder on them. So we can measure that charge, and sure enough, it's 1.056 times 10 to the negative 10th ESU. We multiply that by the bond length, and that gives us our dipole moment, the magnitude of the dipole moment. This is just giving you an idea of how we can actually kind of like determine this number, or where this number actually comes from. So I hope that kind of makes sense. Now, so that is one way that we can measure the polarity of a molecule, is the dipole moment. Another thing that you'll see is what's called the percent ionic character. So that's where we're going to take the dipole moment that we just calculated, and we're going to compare it to what if this were completely ionic. So we're going to keep the distance the same, but we end up actually changing the charge here, because the charge now is going to represent the full separation of electrons. So we're going to take these covalent electrons and we're going to give them to the chlorine. So if we just do that kind of like imaginary thing, what happens? We would end up with a dipole of 8.51 Debye. So then we ask ourselves, what percentage of that carbon-chlorine bond is actually ionic? The way that we do that is we just take the actual dipole moment, divide it by this theoretical 100% ionic one, which was 8.51, multiply it by 100 because it's a percent, and that gives us the percent ionic character. So again, these are just ways that we can measure the the polarity of a bond. We can either talk about its dipole moment or its percent ionic character. Yeah, so just like comparing here, so we have a carbon-oxygen, an oxygen-hydrogen, and a carbon-oxygen double bond. We're looking at the percent ionic characters here to give us an idea of the polarity. So first we'll look at the Debye. So the CO single bond has a observed dipole moment of 0.7 Debye. Oxygen-hydrogen single bond is 1.5 Debye. And then the carbon-oxygen double bond is 2.4 Debye. If we plug in, again, this number, we keep the distances the same as what we had before. So it was 1.41 times 10 to the negative 8 centimeters. We're going to keep that same bond length here, but we're going to multiply it by this charge of the actual electrons. We imagine they're fully separated. So this is going to be our 100% ionic character on the bottom. The carbon-oxygen single bond is 10% ionic. The oxygen-hydrogen single bond is 33% ionic, and then the carbon-oxygen double bond is actually 41% ionic. So just to give you an idea of how we can measure the polarity of these bonds, and it tracks exactly with what we expect, which is where the oxygen-hydrogen single bond is more polar than the carbon-oxygen single. We can see that in electronegativity differences as well, if you calculate those out. And then finally, the carbon-oxygen double bond is actually even more polar than the oxygen-hydrogen single bond or the carbon-oxygen single bond. So now we have to ask ourselves, why is that carbon-oxygen double bond more polar than the carbon-oxygen single bond? I'll give you a moment, you can think it over, and I'm gonna pause the video here. You can pause your video, try to come up with an answer, and we'll pick it up here in just a second. All right, well, I hope you figured out that the most important factor here is going to be the separation of charges here, which is this 2.4 times 10 to the negative 18th ESU times centimeters. And the reason that this partial charge is so much bigger here for the carbon-oxygen double bond is because rather than just dealing with 2 electrons like we're dealing with in the carbon-oxygen single bond and the oxygen-hydrogen single bond, we're actually dealing with 4 total electrons here. So now The oxygen is pulling 4 electrons to itself rather than just 2 electrons to itself. And that's what results in the greater ionic character. We're also going to find out that this carbon-oxygen double bond has pretty significant ionic character when we study resonance in the next chapter. That's a very brief preview of what we're going to talk about. Now, that's not enough. We can't just focus on the polarity of bonds. We also have to consider the geometry of a molecule. And not only do we have to have these polar bonds, they also have to be asymmetrically arranged. So the overall molecular dipole moment is going to be equal to the sum of the individual bond dipoles. Now, you can do this easily as like a vector addition. So here, like if we look at, for example, this is dichloromethane, which is a common solvent. You would normally use it in lab a lot, so you get very familiar with it. Here, what we do is, so if we just imagine, we're going to do this vector addition. Ooh, that's bad. Okay, let's undo, and use the straight line drawer. Here we go. There we go. Much better. Okay. And now we're going to draw these dipoles onto it. So I'm going to start with the one that's up here. So we're going to draw this dipole here. Okay, so it's going to look like that. And we're going to add to it this dipole down here, vector addition. Should look something like that. Okay. Now the sum of those two is just we go from the origin to wherever we ended up, right? So brief calculus review, if you recall this. And so that's what we end up with. We get this little arrow pointing just like that. And that's what we end up with, our net dipole. Now, if we compare that to for example, to carbon dioxide. Carbon dioxide is a linear molecule. So it looks something like this. It's linear, as you know from doing the Lewis structure earlier, and it has 2 dipoles. So we have one dipole, this carbon oxygen double bond pointing this way, and this carbon oxygen double bond pointing this way. Now these dipoles are equal magnitude and they're exactly opposed. So what happens if we try to add those 2 vectors together? They totally cancel out. They go to 0. That's why carbon dioxide is nonpolar. And you can do the same thing here with ammonia and with water. You add the dipoles all together. You do get a dipole from the lone pair. Basically, the lone pair you can think of as like a strong negative charge. So you're always going to point towards the lone pair. Adds together and it gets your net dipole moment. Let's clear all these drawings and let's move on. Keep in mind, you need to know the geometry before you can analyze the polarity in this way. If you don't have the proper geometry, you won't get this part right either. So make sure you go through VSEPR, evaluate the polarity of the different bonds, and then you can find the net dipole moment from there. Another way that we might show you polarity throughout the semester is what's called an electrostatic potential map. Hopefully you've seen one of these before. If not, basically what it is we have a way of measuring the positive or negative charge around a molecule. And so you just kind of map it onto the molecule here. And what we do is we just give you a scale. So here, the negative charges are in red, the partial, like the slightly less negative into yellow, neutral is green. And then as we get more positive, we get stronger and stronger blue colors here. So that shows us here the carbon and the methyl group here is more positive. It's a partial positive charge. And then up towards the chlorine on this chloromethane is partial negative, which is what we would predict since chlorine is more electronegative than carbon. Chlorine should be sucking electrons towards itself. So it's going to have a partial negative charge. This just gives you an idea of polarity of different solvents that, again, normally you would use in lab. This time you're just going to have to understand it this semester. Acetone has a dipole moment of 2.69 Debye, so it's considered a polar solvent. Chloromethane, not a solvent per se, but it would have a dipole moment of 1.87. Water, of course, classic polar solvent, has a 1.85 Debye. Methanol as well, very similar, and then ethanol too. Finally, we have ammonia, which we'd occasionally use, and diethyl ether. We're getting less and less polar as we go down here. Diethyl ether is kind of in the middle of all of our organic solvents. It would normally be considered a non-polar solvent. And then moving on to methylene chloride or dichloromethane, we're getting smaller and smaller dipole moments. Finally, we get to pentane, which has 0 dipole moment. It's completely non-polar. Okay, now finally, this is where things actually kind of come to a head, where we're going to make predictions based on all of that. And that is based on what we've learned about dipole moments. We can actually predict the intermolecular forces that a molecule should experience. And this is going to affect all sorts of properties. So solubility, boiling point, density, state of matter, like at room temperature, the melting point, all of these different things are going to be affected by these intermolecular forces. And as a reminder, we have 3 different types. We have dipole-dipole interactions. Then we have hydrogen bonding, which is like a super strong dipole-dipole interaction. And then finally, we have dispersion forces, which you may have also called London forces. So let's just quickly review what these are. So first up, we have dipole-dipole attractions. This should make sense because what we just saw is that we have polar molecules, and these polar molecules separate partial negative and partial positive charges in one molecule. Well, if you have a bunch of these molecules floating around, the partial negative side of one is going to be attracted to the partial positive side of another. And so this is what's called a dipole-dipole attraction. This is a very strong intermolecular force. This is going to hold these molecules together really well. And this is why acetone is something that's able to actually dissolve a lot of polar molecules. Compare, for example, isobutylene with acetone. So these molecules have almost the exact same molar mass, yet very different properties. So the boiling point is something to point out here in particular. Isobutylene boils at -6.9 degrees Celsius. So it's a gas at room temperature, whereas acetone boils at 56.3 degrees Celsius. So it's a liquid at room temperature. And the only difference here is that we have this carbon-oxygen double bond, which is a very polar bond, whereas isobutylene has no polar bonds at all. There's no dipole moment for that molecule. So that's just one of the many things that's affected by it. But the easiest way to see it is looking at the melting point and the boiling point. Next up, we have hydrogen bonding. Hydrogen bonding, again, is a type of dipole-dipole force, so we don't need to explain it too much, but it specifically has to be between a hydrogen that's bonded to an electronegative atom, so nitrogen, oxygen, and fluorine. Specifically, it has to be a nitrogen-hydrogen bond, oxygen-hydrogen bond, or hydrogen-fluorine bond. And then it has to be, it's a dipole-dipole interaction from that hydrogen to a lone pair on another electronegative atom. The classic example is water, because water, its oxygen has 2 lone pairs that are available for hydrogen bonding. And then also it's bonded to 2 different hydrogens. And so these are able to hydrogen bond to other lone pairs on other water molecules. This is why water is so sticky. It sticks together to itself really well. So you drop your water and rather than the molecules spreading out and evaporating very quickly, instead you get a puddle. The same thing is true with ammonia, although for ammonia, you have 3 hydrogens that are available for hydrogen bonding and only 1 lone pair that's available for it. So just kind of keep that in mind. Yeah, and the reason is, again, you have to have this hydrogen-oxygen, hydrogen-nitrogen, or hydrogen-fluorine bond, because those 3 elements are strongly electronegative, and they have really good electronic overlap with hydrogen. So like your hydrogen-oxygen bond, the electrons are going to be very strongly pulled to the oxygen. So you're going to have these very strong partial negative charges on the oxygen or nitrogen or fluorine, and then you have a very strong partial positive charge on the hydrogen. The other reason is hydrogen doesn't have any core electrons. So when you pull electrons away from the hydrogen, you're basically exposing the nucleus of the hydrogen, which is just a proton. So that's another reason it's such a strong partial positive charge. Now keep in mind, we call these hydrogen bonds, but they're still very weak relative to covalent bonds. They're 20 times weaker, just to give you an idea. Okay, so we have another word that we're going to use. This is particularly useful in lab. We have this protic versus aprotic solvents. The idea is here that solvents that can engage in hydrogen bonding, they have hydrogens available basically. So they have oxygen hydrogen, nitrogen hydrogen, or fluorine hydrogen bonds. we call them protic solvents because they have protons available. If they don't have those protons available, so they lack an oxygen-hydrogen, nitrogen-hydrogen, or fluorine-hydrogen bond, they're called aprotic. This can be very important because sometimes having those protons available is something that's going to stop a reaction. We're going to cover this in chapter 3 in particular when we talk about acid-base chemistry. Yeah, and then also it kind of explains why we see these different boiling points. So here showing trimethylamine, ethylamine, and propylamine. The boiling point as we go from left to right increases very significantly. That's because with trimethylamine, the nitrogen has a lone pair, which can accept a hydrogen bond, but there's no hydrogens bonded to it to give away a hydrogen bond. On the other hand, with ethylamine, that has one hydrogen available for hydrogen bonding. Propylamine has two, so that's even more strongly hydrogen bonding. Hydrogen bonding also shows up in biochemistry. It's responsible for the folding of DNA. So it's what keeps the base pairs together is hydrogen bonding. And then also there's the helical structure, the double helix structure, where you have these interactions in, oh no, I'm sorry, I labeled these wrong. This is the alpha helix of a protein, and this is our DNA. The DNA is held together by hydrogen bonding interactions between the base pairs, and then the alpha helix structure of a protein is held together by these hydrogen bond interactions from one amino acid residue to another. Okay, that brings us to our final and the weakest force that we have to worry about, which is the London dispersion force. So these are basically like very weak forces that can occur between molecules that are nonpolar. Basically what happens is, normally you expect to see the nonpolar electrons to be completely spread out, just totally neutral, flat among the entire molecule. But what actually happens is sometimes there's going to be more electrons on one side than another. It's just like if you shake a bunch of dice, okay? So shake a bunch of dice in a box. Sometimes all the dice are going to end up on one side of the box, and sometimes they're going to be on the other side of the box. Sometimes they'll be evenly distributed. That gives us this idea of this temporary dipole. Now, once we have this temporary dipole where the electrons happen to be on one side of the molecule more than the other, that gives us a partial negative charge. Well, that's going to be seen by the other atoms or the other molecules that are in the mixture. So now this partial negative charge is going to push away the electrons on the neighboring molecule. So this is going to be our temporary dipole, and that induces a dipole in a neighboring molecule. Now this is like very quick. It goes away almost instantaneously before you even see it. But these interactions do exist, and this is what holds these together. So again, it's very weak, but if you have enough of these carbon-carbon, carbon-hydrogen nonpolar bonds, they add up to be very important. For example, you may remember from hopefully when you were a kid, you learned something about geckos. So geckos can climb up like almost any surface. So even glass or something that's totally nonpolar, like the wall, like paint or something like that. And the way that they do it is their fingers have these like long hairs, and these hairs are very nonpolar. But the thing is, they have this huge surface area, and that surface area allows for strong dispersion forces from one foot pad to the surface that it's climbing up. So even though the interactions themselves are weak for each of them, overall, if you add up all of the forces together, it's actually enough to let the gecko climb up the wall. Yeah, and so this is why when we go from butane to pentane to hexane, basically just increasing the number of carbons and hydrogens in the molecule, we increase the boiling point. Because when we go from butane, here we have 4 carbon-carbon bonds and then 10 carbon-hydrogen bonds. Pentane, 5 carbon-carbon bonds, 12 carbon-hydrogen bonds. Hexane, 6 carbon-carbon bonds, 14 hydrogen carbon bonds. The boiling point increases as well from 0 to 36 to 69 degrees Celsius. Again, that's just because we're adding up more and more of these dispersion forces, which increases the boiling point. Okay, now one thing that's a little more difficult to understand, the molar mass thing should be pretty straightforward. The thing that's a little harder to understand is that the more branching there is in a molecule, the lower the surface area is going to be. And so the lower the surface area is going to be, the less interactions you're going to have from one molecule to another. So you're going to have weaker dispersion forces. The best way to kind of visualize this is look at N-pentane versus neopentane. These are both C5H12 molecules here, but N-pentane boils at 36.1 degrees Celsius, neopentane boils at 9.5 degrees Celsius. The best way to think about this is that N-pentane, because it's flat, can stack, N-pentane molecules can stack on one another really easily. Think of it like a Pringle, right? I mean, they're in their tube and they sit flat on one another. On the other hand, the neopentane, they don't stack up well against one another. They have a very small surface of interaction. That's more like a normal potato chip, like what you get from a bag of potato chips. Here, they're all different shapes, so they're interacting very weakly. And so because of that, there's less dispersion forces holding those molecules together. Okay, and then finally, this is the most important and the last slide of the lecture. We want to remember solubility. Remember that polar molecules are going to be soluble in polar solvents. And that's because their intermolecular forces are compatible. Molecules that have dipole-dipole forces are going to be able to interact with other molecules that have dipole-dipole forces. On the other hand, molecules that have dipole-dipole forces aren't going to like nonpolar molecules. So nonpolar compounds are not going to like polar molecules. They're generally going to mix well with other nonpolar compounds. So just keeping that in mind, again, this is a rule of thumb. This is not an absolute rule. You're going to find cases where something that you would predict to be too nonpolar is going to mix with something that you'd predict to be too polar when you go through your lab results later on this semester. But this is our rule of thumb. Polar dissolves with polar and nonpolar dissolves with nonpolar. Okay, so last couple, sorry, that wasn't the very last slide. There's just a couple of things we want to talk about, which is how you can get things to dissolve. So one problem is, right, trying to dissolve, for example, let's say virus particles in water. Well, they're soluble in water, sure enough, but a lot of nonpolar compounds, like fats and greases, for example, aren't soluble in water. So one thing that you can do is actually use something that's got a polar end and a nonpolar end, like, for example, a soap. So a soap here has a carboxylate group and then a long carbon-carbon chain, which is very nonpolar. This nonpolar group can interact with dirt, particles, oils, all that stuff. And this polar group is going to interact with water. And what you end up happening is you form this like micelle form where all the nonpolar tails of these molecules stick together, keeping the dirt in the middle. And then the polar groups arrange themselves on the outside so that that can interact with water. And that allows the water to carry away dirt. So again, make sure you're washing your hands out there. And we'll pick up in chapter 2 with the actual organic chemistry. See you soon.